name is Sarah Ramirez. This is my lab report for Lab 4. This lab was to determine and predict the motion of a spring mass system by comparing the observed motion with a computational model. The results for this lab were that the change in total energy is 0 in the predicted model and observed model are relatively similar, with the y position graph deviating more than. Here are some background concepts before we get into the lab. The first important concept is Newton's second law in the form of the momentum principle, which is used to derive the velocity update formula that is used in the computer model and seen below. It relates to the net interaction between the system and surroundings too. The observed motion of the system, the formulas below were used in the computer models, predicted the motion of the object over time. Another important concept is the energy principle, which states that the change in energy of a system is equal to the work done on the system by the surroundings and the exchange of thermal energy between the system and the surroundings. The main force involved in this experiment are force of gravity and spring force. Their formulas are shown and used in the computational model. In the experiment, the system was a mass, earth, and spring, and the surroundings were nothing, as I included everything in the system. I chose the tracker model so that the origin was at the fixed point of the spring, and the y was collinear with the spring the y-axis was collinear with the spring at rest position. I tracked the model from the beginning when it was released from hand, and this model I assumed there to be no friction or air resistance, in other words, no work done by the surroundings. I also assumed the calibration length, mass, spring stiffness, and relaxed length from the video lecture. Here are some of the initial conditions I set in my computer model. So the mass I set to be 402 kilograms, as it was 0.402 kilograms as it was given in the video. The initial position to be 12 meters in the x direction, the negative x direction, and 6.67 meters in the negative y direction, as obtained from the video, from tracker. The initial velocity to 0 meters per second, as assumed that the mass starts from rest, and the constants found using the formula shown and also given in the video are below. Finally, I set up some equations that were used in the calculation portion of the code. In this section of the code, I first established initial energies when I calculate Fnet, which is then used, and the position and velocity update formulas in order to update the mass's velocity and position the mass's position. Position is then used to update the spring length, and finally the mass's velocity, position velocity, and the spring length is used to calculate the energy changes. This code basically predicts a feature using the initial codes I provided and provides the theoretical data later graphed. There are 3 graphs produced from the GlowScript code. The top 2 graphs compare the model versus experiment with the X and Y positions. The bottom graph compares energy changes, errors causing deviation between the model and the experiment, are tracker errors by not consistently marking the center of the mass video, perspective differences resulting in incorrection calibration into outside forces, and energies such as drive force and thermal or rotational kinetic energy. Comparing the top 2 graphs, there are differences in the amplitudes of the y position model versus experiment, which can be attributed to the errors discussed previously. Specifically, errors such as not consistently marking the center of mass, incorrect calibration, and not considering outside forces such as drag force, as all those forces affect the y direction. Both graphs have similar oscillation periods and shape when comparing the model and experiments. In the exposition graph, there is a deviation as time increased, which makes sense because the spring constant was calculated with an average of the first 3 oscillations. Therefore, it becomes less accurate as time increases. So the energy principle satisfied looking at the change in energy graph. The energy principle satisfied the total change in energy. The sum of the kinetic, gravitational potential, and spring potential is 0, which follows the energy principle, as the change in energy of the system should be equal to the work done by the surroundings, and since we have no surroundings in our model, the change of energy should be equal to 0. And then estimating the oscillation periods. From the tracker data, we don't find that there is a difference in periods between the X and Y positions by about 0.127 seconds. The difference in periods could cause the deviations we saw in the GlowScript prediction, since the spring constant was calculated using T or period, and this difference could be caused by outside forces and inconsistency when plotting in tracker. Thank you.